polynomial method. What? Okay. I will mainly focus on polynomial method and mainly on two of them. So I start with the reason for solving the Helmholtz equation, and from which such kind of problems come from. In fact, the need to solve the Helmholtz equation comes from the high demand for numerical simulation of wave. And this demand is coming from several scientific and engineering activity. I list some of them. It is just a short list.
Désolé.
Okay.
Ouais.
And
bien. Abderrahmane, peux-tu remettre le son? Je l'ai désactivé par erreur.
you hear me?
Yes, yes.
Do you hear me? Okay. And the need for this numerical, from the need of this numerical simulation, there are a large amount of research activity done by large size teams working in top university and institute. And but not only, also there are a lot of research activity conducted in this area in industrial company, for instance, oil company, car company, and so on. For instance, in France here, there are three major companies which have large teams working in this topic. For instance, not for instance, the three major companies are Airbus, Total, and Dassault Aviation, and also CNES. I choose to focus on to illustrate this talk on this problem. It concerns the seismic imaging. In fact, and a very particular part of such activity. And we will focus on the solution of the direct problem, of the so-called direct problem. What does it mean? A campaign, an imaging, a seismic campaign consists of launching waves. Those waves are reflected by the medium, by the subsoil, and are collected by receivers here. And the data of the receivers constitute a seismogram, an actual seismogram. And the solution of the direct problem consists of you start from an expected or an anticipated medium, and given the emitted wave, you reconstitute by calculation what the signal received by the receivers, and you then obtain a synthetic seismogram. And by adjusting the synthetic seismogram with the actual seismogram, you try to reconstitute the configuration of the subsoil. And a main step hence is to have a synthetic seismogram. How to obtain this synthetic seismogram? You have to solve a realistic assumption. It is not unrealistic here. Are constituted by the equation of propagation of elastic wave. And the usual assumption is that the gravity force can be neglected. The medium is initially at rest, and that is an isotropic medium. And so you have to, from the boundary data, from the transmitter, you get the boundary data, and from the boundary data you compute the synthetic seismogram by solving this problem. And the configuration of the medium is given through the data of the Lamé coefficients here, two piecewise constant function, and you have to solve this problem. But this problem is a system, a set in 3D. It is too large to be handled, even by supercomputing. So usually, people do a reduction of this model and consider the acoustic approximation. What is the acoustic approximation? Perhaps some of you know what it is. It is based on the separation of waves. In fact, it can be separated, but to understand the construction of such a model, of such a reduced model, you have to know how the wave can be decomposed in two parts: a primary wave, which are compressional wave, and secondary wave, we are shear waves. And this wave can be separated only on an homogeneous medium. And to separate them, in fact, you rewrite the momentum equation in this way through the two differential operators, grad G operators, and the double curl operators. And to get the P wave, you apply the grad G operator to both of the two hand side of this equation, and you get, and when you apply the grad G, since the divergence of a curl is equal to 0, you only the grad G term remains in the equation, and you obtain that the grad G part, the grad G of u, satisfy a wave equation propagating at the velocity Cp, which is the velocity of primary wave of compressional. And next, when you apply the curl to this to the equation, since the curl of the gradient is equal to 0, you get here too a wave equation, but this one's the curl of u is propagating at the vitesse cs, which is at the velocity cs, and cs is the velocity of the secondary waves. Usually, Cp is at least 3 times larger than CS. And how the wave is decomposed? So we will start from this very standard, very classical relation in vectorial calculus. The vectorial Laplacian, you can decompose it as a grad G of U minus the double curl of U. And in this way, you invert in a formal way the Laplacian, and you see that you can decompose U in a P wave, in a primary wave and a secondary wave. Of course, this P wave and S wave are coupled when they cross, for instance, discontinuity, when the wave crosses from one medium to another medium, or when they hit the boundary. And how to obtain the acoustic approximation? In fact, to obtain the acoustic approximation, you go back to the relation between the strain and on the stresses and the strain, and instead of expressing this equation in terms of the Lamy coefficient, you express it in terms of this two velocity, the primary velocity and the secondary velocity. And then you put CS equal to 0. That is, you completely neglect the secondary waves. And when in this way, you see that the only part in the stress that remains is this part, and you see that this part is in fact is a relation which characterize the computational wave. And so it is quite natural to describe, the stresses by only a pressure, since the stresses are only computational by the pressure. And dividing by rho, you get that the pressure satisfies a wave equation with varying coefficient here. Usually one can assume that rho is constant, as in fluid acoustics. And for instance, and then you obtain a wave equation with the Laplacian here, and with the varying velocity, and the medium is characterized by this velocity, which are piecewise constant. And in fact, you have initially you have a boundary condition on U, on the displacement E, but you can easily translate them in terms of boundary condition on P, for instance, but they transform on one type to the other. For instance, if you have a Newman condition on U, it transforms in Dirichlet condition on P, and reciprocally, if you have a Dirichlet condition on U up to two-order derivative on U, you transform it in a Newman condition on P. And so you are led to solve a mixed initial boundary value problem on the pressure only, that is only one equation, one one unknown instead of three, the three component of the displacement. Usually, well, not usually, but a lot of work have been devoted to solve this equation by a time marching method. That is, you take a grid of time grid, and then you, from the initial condition, you solve step by step this time this time domain equation. Another approach is instead which seems more accurate, is to do what follows. In fact, you extend p by 0 for the t for negative t. P tilde is the extension of p by by 0 for negative t, and you take here the in fact it is not the Fourier transform, but instead the inverse Fourier transform. It would be equivalent to take the Fourier transform, but it is more convenient to take the inverse Fourier transform, because after you have a bit more convenient way to describe the propagation of wave. And since you have zero initial condition, the second derivative of p are nothing else than the extension by 0 of the second derivative of p. And then you can take the Fourier transform of the equation, and you obtain that each of these Fourier component is solution of an Helmholtz equation, with here kappa is equal to omega. It is the variable in the Fourier domain, divided by Cp, and this is the wave number of the equation. In fact, I started from zero initial condition. If I started from non-zero initial condition, I would have only here right-hand side volumic sources which result from the initial condition. Perhaps it is not, this writing is not completely correct, but I will correct it in the final version. And so doing a fast Fourier transform, an inverse fast Fourier transform from the solution of the Helmholtz equation for the selected omega, you can reconstitute the solution. And in this way, for instance, you can focus on really the frequencies which are important in the solution, and not solved by the time marching method. You solve for all the frequencies, but by this method, you can focus only on the important frequency, on the frequency which compose the solution. And also, you see that since this problem are independent, this method you can parallelize the calculations. You can launch the calculation of each of the solution U omega on some processor. It is completely independent each from the other. So this method has several interesting property, and becomes to be used intensively used in the And you can remark it is important to remark that this u omega is a component of the Fourier transform, and u omega exponential minus e omega t is a solution of the wave equation. And in this way, I come where are the difficulty of solving such an equation? And mainly, I consider in this talk, I consider the model problem. The model problem is considered in all these studies, theoretical studies concerning this problem. So I suppose that I am in one dimension and normalize the length of the domain. And I assume that the coefficients are constant. And I obtain this very simple problem, but it is featuring the main difficulty of the solution. And its explicit solution, I can compute its exact solution, and its main solution is a sinusoid exponential e kappa x. And a sinusoid has a sinusoidal oscillation. And if you, for kappa is equal to Pn, for instance, the solution does n oscillation in the interval, in the computation interval 0, 1. So since the solution oscillates, you must, for large K, you must have a large density of nodes to correctly represent the oscillation. You are first with one difficulty. You have oscillation. You have to correctly represent the oscillation. So for representing one solution, you must have a correct number of nodes. And also you may have several oscillation, and so the problem becomes very large. And it is the first, but it is not the only difficulty of the problem. For instance, if I consider first finite element solution of this problem. You express variationally the equation. It is expressed like this. It is quite classical. But you see that for this problem, you have 3 bilinear forms. The first one is a positive bilinear form, symmetric positive linear form. It describes, in fact, the potential elastic energy. And you have a second bilinear form, it is the kinetic energy. And the third bilinear form, which has a purely imaginary, and the difficulty comes from the bad sign here. So you can not have coercivity. And it is not a bad thing in something, in some meaning. It is quite natural, because it is the principle of functioning of this system. Since for the propagation, for the wave to propagate, you have this, the sum of these two terms is called the reactive energy. And in fact, it describes the fact that you have to put an amount of energy for the wave to propagate. It is called the reactive energy. And this energy is divided in two parts: a potential energy and a kinetic energy. And during the propagation, there's two energy convert each to the other. Without this conversion of energy, you cannot have propagation. And this term here traduces an absorption of energy at the boundary. Otherwise, for instance, if you have not this term, you can have resonances, for instance, that is system which are functioning without dissipation of energy and with a continual conversion of energy from one type to the other type. And this constitutes a real difficulty in the solution of this type of problem. And difficulty in the solution and difficulty in the analysis also of the problem. The first difficulty is the stability. Even at the continuous level, the stability of this problem is not straightforward. It is obtained only by argument based on compact embedding and so on Fredholm alternative and etc. And you find again all this difficulty at the discrete level plus some other one. And in fact, the first breakthrough for the analysis of the stability of this problem probably was made by Sachs in an article in 74. By a technique, by a very interesting technique, which was used later for much more elaborate estimate. And after all this, contrary to static problem, for instance, the stability is not guaranteed for independently of the mesh. What you establish is that the discrete problem is stable under a minimal resolution condition. That is, your mesh size must be less than maximum mesh size, and unfortunately, H0 is not explicit. Here I show you recent calculation here by a method, not this method, but by a more elaborated method called hybrid finite element method. When you see this, minimal resolution, you exhibit this minimal resolution condition. For instance, here, the method converges with the right scale of convergence only after when the mesh size is less than this value. And before that, the error has a completely erratic behave in a completely erratic way. And when you I pass to the second difficulty of the first. We have listed two difficulties. The first one is the high number of degree of freedom to correctly represent the solution. The second one is this mesh resolution for usual finite element method. And there is a third one here. For instance, for when kappa is relatively small, that is here kappa is equal to, when n here is equal to 2, the solution oscillates two times. The solution you obtain here is, the approximation is conforming with the error error approximation by polynomial. Use a polynomial of degree 1, and the solution is with the density of 24 points per oscillation. You get correctly the solution with an error less than 3%. But if you augment k, but maintain the density, and you have here too, you have 24 nodes per oscillation. But you see for 100 oscillation, the solution, the error becomes completely wrong. And this is due, in fact, to a difference of in the speed of the oscillation. The computed wave has a delay, oscillate with a delay relatively to the real wave, and this is a real problem for this kind of propagation. When you compute the solution over large of domain of large size in terms of the wavelength, you have a phase error here, which destroy the quality of the solution, and this is called the pollution error. Earlier result, convergence results show that if you have a condition, for instance, here for H, you take 24 nodes per wavelength. This is the you get the approximation, the correct approximation, but in order to deal with the pollution error, in this paper, it is shown that you have to get much more. For instance, for kappa is equal to kappa is corresponding to 100 wavelengths. You have to take a mesh size 100 smaller than and so you obtain this paper gives a theoretical result, which shows that how you can eliminate the pollution, but the cost it is not it cannot be used in practice. It is it gives rise to overmeshed domain. And the first big breakthrough was done by Babushka and Eilenburg in 95. And they show that the error, in fact, for the model problem, but it can be anticipated for much more complicated problem. Excuse me. The error is a superposition of two types of error: the approximation error, which is the usual error in the finite element approximation, but another term they call the pollution error, and it is in this form. In fact, it is kappa square h kappa third h square. And you see that if kappa, you explain the previous result. If kappa is not too large, it is that this term, the approximation error, which is preponderant, which is dominant in the error, But when kappa become large, the approximation error is dominated by the Paulician error. And this result was extended more than 15 years later by Melenc and Sauter to multi-D. And then what the first way to face the pollution error was is based on one observation, is that considering finite element method with higher order, significantly reduce the pollution error. For instance, here, if you consider the same problem with the 100 wavelength, but at degree 2, but keeping not augmenting the size of the system, keeping the same number of nodes per wavelength, and you see that you eliminate here, you eliminate at least you reduce, you significantly reduce the pollution error, and there is no phase error. And for instance, here for the one polynomial of degree 2, the error grows at without limit, and for degree 2 it grows but more moderately, and for even larger degree, for instance for 4 and 6, the error, the pollution error is completely rubbed out. And you can understand why high order method eliminate the pollution error, because in a second paper in 1997, Babushka and Illenberg, for the model problem, have proved that this once the error is dominated by the approximation error and this term, and for p sufficiently large, this term become dominated by the approximation error. And this estimate was extended by Melenc and Sauter to multi-D problem in 2010. And if we do a summary of high order method, their advantage that they can be implemented by standard finite element code. They significantly reduce the pollution error, but they has a failure. Failure is they are hard to manage, especially in 3D. Why? Because you face a difficult numerical integration problem. For instance, on a triangle, you have not really real numerical integration formula for degree more than 13. But also the matrices become denser, and so the problem become much hard to solve. And the discrete problem is you are not sure when you use a scheme, you are not sure of your result because of this minimal resolution and condition. And they reduce but not completely eliminate the pollution effect. And so I pass now to some other method for facing the failure of the high order finite element method, the anterior penalty DG method. I have only, what time I have? I have 5 minutes only?
Oh, yes, 5 to 10 minutes.
5 to 10 minutes. Okay, thank you.
You can, yes, we can continue for 10 minutes, yes.
Oh, thank you. And the principle, you have a mesh also, like finite element method. It is agreed here. And the principle of this method is to approximate U and to take test function which are discontinuous at the interface of the element. They are polynomial but discontinuous at the interface, at the junction of the intervals here. And for the derivation, I will say some words about the derivation of this method. You take the equation and multiply it by V, so no problem, and integrate by part. But for integrating by part, since V can be discontinuous at the junction, you have to decompose the integral in a sum of in sub intervals. And you obtain this formula.
Sorry, Abderrahmane. IP is for
okay.
The abbreviation.
IP is for okay, so I have anterior penalty DG.
Okay, thank you.
Anterior penalty DG method. Okay, so it is just, I go faster. It is just integration by part, the main integration per part, and you rearrange the term in the first term and write them in this way. So you get this equation. And since you plan to use a completely discontinuous function, you use this relation. That is the value of at a junction of the solution is equal to its mean from the left and the right, and its jump is equal to 0. And in this way, you can rewrite this the equation in this way and add some terms. The important point, and thus you can add some terms which are consistent, that is, which are equal to 0 for the real solution. And then you obtain this this equation. Perhaps it is not okay. And you stabilize the equation, and here is just a rewriting of the equation after integration by part. And the most important part is to add the penalty term. And you have here two kinds of penalty. You penalize the jump, and you penalize also the jump of the derivative. But you see here, but you penalize the jump by a large term. It is alpha over h. H is the mesh size. This is a small number. But here you have to penalize this, the jump of the derivative by only a small term. Usually, EPDG use alpha real and gamma is equal to 0. But the progress here done by Feng and Yu is to take alpha in the form of an imaginary, that it is easy to understand here, to take the penalty term in the form of an absorbing, of energy absorbing terms for alpha, but for gamma. And for gamma to consider also a real pair. And the real pair can be considered as a mass added term at the junction. And they be able to analyze the problem and prove stability and convergence. But it seems that their estimates are not optimal because for usual computation, you find that the method has the same order of convergence, at least for gamma purely imaginary, for alpha purely imaginary and gamma purely imaginary. You get the same order of convergence than an usual finite element method. And you may ask, what is the gain here? If the gain here is first that for this problem, the discrete problem is always well posed. There is no minimal resolution condition. So for anterior penalty method, the discrete problem is well posed, whatever the mesh you consider. And also it is stable at it is not the stability is not mesh dependent. It is the first interesting fact about this method. But the most interesting thing, it's unfortunately it is only empirical. If you take a correct, it is very sensitive to this parameter. If you take a real pair for gamma and it is chosen in the right way, so you eliminate completely you see here the finite element solution. You see the pollution error, that is the error, the phasis error, and the EPDG method coincides with the exact solution. So by adequately choosing the right pair of the gamma parameter, of the parameter, the penalty method of the derivative, you completely rub out the pollution effect. And a very useful research topic will be to be able to avoid an empirical determination of gamma. It would be of very interesting help for improving this method. You have I say current method. There are a lot of other methods used to solve the Helmholtz equation due to its importance. You can use a finite element method with special basis function to reduce the pollution effect. The partition unity of method, TERF's DG method. TERF's DG method is DG method, but instead of using polynomial, you use local solution of the Helmholtz equation, for instance, plane wave. This DG method with but when you construct the local function by boundary integral equation, reduce the pollution effect. And the ultra-weak variational formulation, which is a particular but very special method, part of third degree method. So I have finished. Thank you very much for your attention.
Thank you very much, Abderrahmane. Thank you for this introducing lecture for solving Helmholtz equations and especially for numerical difficulties. Is there some question? No question? Okay.
I have one, Nabil.
Yes, Makram, yes.
Thank you. Thank you, Professor Bendali.
Thank you.
This presentation. It's a small question about when we have the large wavelength. Is the problem located near the boundary or inside the domain also?
No, yes. In fact, the problem is not located. For some problem, you may have a problem located at the boundary, like for instance, for what is called, I don't remember, when you have wave propagating, concentrating on the boundary. Do you remember, Nabil, what is this kind of wave?
It's not Foucault problems, no?
No Foucault for elastic wave. It is only for elastic wave, not for acoustic
okay.
wave. Okay, it is wave which is concentrating on the boundary. But it is a very special kind of wave. It is occurring in Earth quartz, for instance, but not in, for instance, in seismic imaging. Here, the problem for large wavelength comes from an error induced by the numerical mesh between the real wave number and the numerical wave number. Do you understand?
Okay. Yes. Mm-hmm.
For instance, the real wavelength is propagating. If you take, for instance, a plane wave, a one-dimensional plane wave, it is propagating with wave number k. That is, it is written in the form E kappa x. Okay? Mm-hmm. But what you calculate is E kappa h x. So you do an error kappa h.
Yes.
The wave which is propagating is kappa h instead of kappa. Okay.
Yeah.
Yes. If you have only one or two, and the error on kappa between kappa and kappa h is the finite element error. For instance, if you are using degree 1 method, the error between kappa and kappa h is only in h2.
Mm-hmm.
So if you propagate the wave on, for instance, 2 or 3 wavelengths, the error is the same as that of the finite element method. Okay, it is not very different. Okay, but if you propagate the wave along, for instance, 100 wavelength, and so the difference become more and more important because you have a phasis error which becomes more and more important.
I see.
Okay.
Yeah.
We start at the same for instance, you start when the wave is at the top, and then it decreases, and then it oscillates. You have a small difference between the two wave numbers. For the two first oscillation, you cannot distinguish them. You have an error, which is the finite element approximation, of the order of the finite element approximation. But after, say, 10, this error is multiplied by a factor 10. Is powered to the factor 10. Instead of having exponential e kappa x, you have exponential e kappa h x. You have exponential e, for instance, for the numerical wave, say kappa h is equal to kappa plus delta k, okay? For the, if x and the difference is equal, the actual wave is exponential e kappa x, the numerical wave is exponential e kappa x exponential delta kappa x. If x is small, exponential e kappa delta x is approximately is equal to 1. But if x is large, delta kappa x, even if delta kappa is small, may become large, and so you have a large error. Not on the modulus, but on the phases. Do you understand? Perhaps in front of a blackboard, it would be more simple to explain.
Yeah, but I understand now better the situation, the difficulty, in fact. I was thinking it's not similar, but let's say that what we can have when we have singular perturbation problem, we have a small parameter and we have the h, which is small. So there is like this competition between the small parameter and the time step, which is h. Here, it's somehow maybe similar to that, but not really, because of this penalty term, I guess, right?
Mm-hmm.
You have like.
I don't think so. It is not.
So it's kind of penalty.
It's not a matter of small parameter here. The difference is really a difference between an error on the phases. The error on the phases depend on an error on kappa, and kappa is the wave number. If the error on kappa is small, because it is the property of the finite element approximation. But if you take exponential e delta kappa x with x large, this term is not close to 1. It is some other complex number of one modulus, but not equal to 1.
Mm-hmm. But this is just for
effectively, it may be an interesting idea to see this problem through a singular perturbation technique. Perhaps.
You have another question, Makram? Makram? Okay.
Yes.
You have another question, or you finished?
No, thank you so much. Thank you for the clarification.
Okay. I have
welcome.
Kappa is the wave number, of course, huh?
Yes. Yes.
Okay, and kappa is fixed, but what do you call the numerical wave number? How you define? You say that there is a difference between the true wave number and the numerical wave number.
Yes, in some when you for the model problem and in some simple computation, you can exhibit the analytical solution of the discrete problem.
Ah, okay, okay. And then the wave number is the wave number of the numerical solution.
Yes, well,
The
yes.
explicit.
And in this way, you can understand what is happening.
Ah, okay.
Why you have such
okay, I understand.
You see that the solution is propagating with a different wave number, close, okay, but not exact, but not equal. So for along small distance, there is a small difference, but along a long distance, this difference become very large.
Okay. Then the error is, come from the discretization and not from instabilities of the calculations.
Yes, it is a kind of instability, in fact.
Okay.
It is a kind of instability. Usual method, like finite element method, IPDG, but without the right coefficient, but the right coefficient are difficult to find. The solution you compute is a numerical wave, but with only an approximate wave number. And the actual method, the list I gave at the end of the talk, all tries to reduce this error. To reduce the error, not to reduce, that is to have a wave where the error is only is limited only to approximation error and not to this phases error.
Okay.
That is a wave, a numerical wave, which propagates at exactly or a very, very, very accurate approximation of the real wave number, and not that is the approximation of the wave number is much more accurate than the approximation of the function of the circle.
Okay. I have another question.
Okay.
I think that these estimation of the error are obtained for a problem in bounded domain. Did the same estimation is obtained for problem in bounded domain and for an approximation with boundary element method?
For boundary element, the Polish error is much lower for boundary element method than for because in boundary element method you use the real wave number, okay, in the computation.
You mean that if you make the same thing, you compute the numerical wave number, you will find the same value?
No.
For boundary element method, I mean.
Yes, boundary element method, roughly speaking, in boundary element method, the numerical wave propagate, since they are represented by the green kernel, they propagate at at the real wave number and not an approximate wave number.
Okay.
The boundary element method, it is not a proof, but there is, I think, recently one proof of this, one rigorous proof of this, that but that can be explained more simply, that when you make a calculation with the boundary element method, you integrate the phasis term in the equation through the kernel. The kernel is, for instance, in 3D, it is exponential e kappa x minus y under. Okay.
Okay.
The wave number is integrated in the equation and in the expression of the solution. Okay. The solution is expressed in terms of the kernel multiplied by the density. So the error you make the error only on the density, and the error is the finite element error is the approximation error. So your error is only an approximation error. There is no phasis error. Do you understand me?
Yes. Okay. Is there other questions? No.
This is time for more questions if you want.
These last years, I see a lot of new papers who use deep learning methods to solve partial differential equations, and especially Helmholtz equations. Do you have an idea about these papers, and do you think that it's an alternative to finite elements, or something that can, in some cases, have had an add value for finite elements methods?
I cannot answer this question. I have not considered this kind of.
You don't see these results, huh? Okay.
No. I concentrate on on hard method.
Okay, thank you, Abderrahmane. Is there other questions?
Thank you for your invitation, and one more time, excuse me for my bad English. I think
no, it's perhaps for me it's easier to follow. It's
not for the other. I think
very close to French then.
Very close to French, yes.
No, I was kidding. No, it's
thank you, Nabil. I hope see you again soon.
And for our attendance, there is the second talk for Abderrahmane Bendali for ultra-weak formulations to solve acoustic and electromagnetic problems.
The same equation, the same type.
Thank you, Abderrahmane. Thank you for accepting our invitation. Thank you for
the invitation.
Very beautiful talk.
It's very pleasure for me to give.
Thank you very much. And I'm waiting for the slides. You can.
Okay, I correct some 2 or 3 things and I send them to you.
Okay, thank you very much. Thank you everybody to following our webinar, and you are welcome for our next talks. Goodbye.
Thank you.